So in this video, we're going to start combining what we've learned so far with Newton's laws of motion with some of the stuff we've learned from kinematics. So here we're looking at some tension problems. So in this video in particular, we're looking just at the tension problems. There's another video where we're going to start combining those 5 key equations and then our dynamic stuff. So let's just review that a tension is a pulling force exerted by a rope or a string. And we're going to make some assumptions here. We're going to assume that all ropes have no mass, so we don't have to incorporate those. And this second picture is showing us a pulley. We're going to assume that pulleys are frictionless and again are connected with a rope. And what I want you to notice is that we have a cart and the tension force here is going forward and the pulley has a tension force going up. So pulleys are really just simple machines whose main function is to change the direction of the tension force. It doesn't actually change the force of tension, it just changes that direction. So let's look at this. Each object has a force of gravity of 140 newtons down acting on it. Determine the tension in each case. So since our Fg is the same, our tension force is going to be the same in both cases. Just here with our pulley, the pulley has changed the direction of the force, okay? So really we only have to do one calculation. So we'll do it for the hanging object. So we have our Ft and we have our Fg. We are going to assume that this is not moving, okay? It doesn't actually tell us that explicitly in the question, but we're going to make that assumption. So we're going to do Fg minus, let me just erase that. We want F net equals Fg minus Ft, just like those other questions we were doing. And if we assume it's not moving, then we have an F net of 0. We know our force of gravity is 140 newtons. And so if you rearrange that equation, Ft is going to go on the other side. And we get 140 newtons. And our F tension there is going to be up because it's going to act opposite our force of gravity. And so in part B, the force of tension is the exact same. We're just changing the direction of the force. So more often than not, you're going to see tension problems where you've got sleds that are connected together or train cars, something of that situation. So in this question, we're looking at 3 sleds being tied together and they're being pulled east. So we have an icy surface. So that means we're going to assume that it's frictionless, which is nice. In just a little bit of time, we're going to be looking at what force of friction does to things. And we're given all of our masses. So, and we're just going to change this so that it's 6.0 kilograms. Okay, just so when we're doing our sig figs, we're rounding to 2 sig figs as opposed to just 1. So in part A, it's asking us to determine the acceleration of the sleds. So all of the sleds, regardless of their masses, are accelerating forward at the same rate. So what we're going to do is we're actually just going to draw a free body diagram. So we have our applied force. We have a normal force, of course. And we have a force of gravity. And our masses are going to be all 3 sleds. So we actually want to calculate a total mass here. So we've got 11 kilograms, 10 kilograms, and 6 kilograms. So our total mass is 27 kilograms. So that's the total mass that we're accelerating, and all of those sleds are experiencing an applied force of 120 newtons. So I'm just going to give myself a slide here. So our F net is going to be equal to FA, and our F net we can always replace with MA, and we're being asked to figure out our acceleration, so we would want to divide both sides by M. So A is equal to our applied force divided by our mass. So again, we're doing all of our sleds because they're all accelerating. They all have the same applied force, so they're all going to have the same acceleration. So we would put 120 newtons divided by our 27 kilograms. And so we would get 4.44 meters per second squared, which we're going to round to 2 sig figs, so 4.4 meters per second squared, and they are going in the easterly direction, so that's going to be our acceleration. So that's the rounded to the correct number of sig figs, but when we do future calculations, we're going to use an extra sig fig just to help us make sure that our answers are as accurate as possible. So the second part is asking us for the tension in rope A. So if you just go back to your picture, you've got your 3 sleds, and we have, that's our A, this is our rope B, and then we have our applied force, okay? So just a little quick diagram. So if we're looking for our tension and force in rope A, we're just always worrying about the masses that are behind whatever rope it is we're calculating. So we're going to draw our FT here. Again, we're going to assume that we have no friction, and our mass for weight 3, or our sled 3, sorry, is 6 kilograms. So that's our free body diagram. So we have F net equals Ft, and we can put MA in for F net, Ft equals Ft. So if we divide, oh, actually, sorry, we don't have to divide at all. So we have our mass, 6 kilograms, and we calculated our acceleration at 4.4 meters per second squared. So that will give us our force of tension. So when you do that, you get 27 newtons, and our force of tension is in the easterly direction because it's towards whatever is holding the rope. So that is our force of tension in rope A. So let's just put a little A there beside our FT so that when we calculate our force of tension in rope B, we'll know the difference. So the third part is to calculate the tension in rope B. So behind rope B, you have sled 3 and sled 2. So here's our force of tension B. So our masses are going to be the 10 plus the 6 kilograms. So our mass is now 16 kilograms. So F net equals FTB. We're going to put MA in. And then we can just put our information in. So we have 16 kilograms. Our acceleration is still the same, that 4.44 meters per second squared. And that's going to give our force of tension in rope B. We want to round that so that we have 2 sig figs. So we get 71 newtons in the easterly direction because force of tension always acts in the direction that it's being held. So we get 71 newtons east. So that is just an example where we're using ropes. Those tension problems can also exist between rail cars, and there's an example of that in your textbook. So hopefully this has helped a little bit with the force of tension.